All right, can you hear me? Fine. So I am Andy Ogielski. Good morning, everybody. And Jim Cowie is somewhere out there. Please wave, Jim. And please hang on with us because at the end we'll tell you how you can join this collaboration and look at your data as well. So we have been exploring and I think succeeding in finding ways to look at very many ongoing BGP sessions dynamically in near real time. And we have found some strange things coming from Redmond, among other things, or related to Redmond. So here is the outline. Generally, people who study large dynamical systems have pretty well-founded claims that if you build something very large and very complex, and it's not, so to speak, genetically engineered, it's engineered by humans directly, these things tend to fail. So we will define a global routing instability. There's a lot of talk about it. We'll give you a clear definition. We will analyze peering sessions from something about 150 peers. That's the right remote root collectors setup that was mentioned earlier by Dave Meyer. And then we'll paint you graphically and analyze instabilities that were caused by Code Red 2 and Nimda worms. And we'll also show you some more familiar instabilities, such as, for instance, caused by router misconfigurations, and show you that they have a global reach and can last hours as well, sometimes days. So let's go on. In this talk, given the time constraints, I will talk mostly about data taken from the RRC00 collection point at Amsterdam right NCC location. And the reason is that that's an interesting collection point because it has multi-hop external BGP feeds from Tier 1 providers and other large providers in Australia, in the United States, and in Europe, and also in Japan. Currently, RIPE has 5 or 6 collection points, 2 in Amsterdam, Vienna, Paris, Geneva, London, and the new one in Japan. We have analyzed them all, but I'll talk mostly about Amsterdam NCC. So anyway, for people who look at traffic, it's customary, so to speak, to look at the rate of message arrivals and then do various things on it. For BGP, it doesn't quite work. I mean, you can see big spikes. Here we see at 30-second bins, so occasionally collecting all message traffic to the RRC00 collection router, we may get something like, 50,000 or 100,000, say, messages coming from 12 peers per minute. They're big spikes, but they are not terribly informative, right? We really have to look what's inside, because that's where the meat is. So let's look at a different way at the same set of messages that I showed you. Again, aggregated. That's from the point of view of all BGP messages coming to the router. Now I plot it on a logarithmic scale. Look carefully. And notice what happens. It sort of goes da-da-da-da-da. If you look carefully, you would see weak diurnal cycles. Kind of cool, okay? People screw up with the net and they go to sleep. And then on September 18th, it goes like kaboom, okay? In 2 hours, there is about 20-fold growth, and if you look more carefully, it's exponential growth in the rate of prefix announcements. And then it lingers and sort of slowly, exponentially decays over 4 days. Now, that's bad, but at this level of aggregation of data, we can't tell if it's global or it's just some local problem, okay? And we have to tease the data apart at a much greater level of detail. So what we will look at, we'll start looking at behavior and correlating data among various peers at different peering points. We'll look at, is there something specific about origin ASs, say, that causes instabilities? Are there some special sets of prefixes that cause instabilities? Are there some special prefix lengths that cause instabilities? And then we'll also look, hey, maybe the route lifetimes change a lot, and we have a lot of very short-lived routes during instabilities, and otherwise everything is fancy-dandy. And that's sort of a big picture of how we analyze the data. And again, I will not show you everything. We can sit down after the talk time permitting, and go over some details. So let's look first, how does it look when I show you all peers of the RRC00 collecting router at Amsterdam NCC, RIPE NCC. I will explain how to read these plots, because I will go through them several times. First of all, the x-axis, meaning horizontal, is just time. I hope you can see that this shows the week from September 10th, actually more than a week, 10 days from September 10th through September 20th. Thank you very much. Actually, I prefer not to exactly maybe show, because people in the back may not see. But this is the time axis, okay? Here on the z-axis, we just show the number of prefixes announced by each peer in 15-minute intervals. That's a 15-minute rate. Now, y-axis is slightly abstract, and look at it this way. The data is arranged in rows, or like hedges, one hedge after another after another. Each of these rows represents the BGP message traffic, and specifically the number of prefix announcements from one particular peer. So you can see that at the time shown here in September, the remote route collection box at RIPE NCC had 12 peers at this moment, okay? One row, one peer. I have anonymized them, but it may not be necessary for this audience, but we know exactly who is who, okay? Now look at something funny. If there is a phenomenon or a BGP event that happens, so to speak, on a global scale, then it should be reflected in announcements, or generally speaking, update messages from most major transit and most major other networks. Otherwise, it's localized. So if something happening simultaneously across very many autonomous systems, or in this case, peering sessions from those autonomous systems, and as I recall, they are big guys. There's Vario, AT&T, Global Crossing, and so forth. It will show as waves going across. And hell, they look like waves, okay? There is something that's happening here, something that's happening here, but something really big is happening here, okay? Notice the scale. The scale is really tailored to the highest peaks, which are isolated events. But this wave here, you see, is quite large. It starts on the September 18th, and it goes on in this figure for about a day and a half. But in the previous picture I showed, it really goes for 4 days. So there is some very long-tailed, very powerful events. What is it? Well, you know what is it, but I'll tell you how we find it. This is separately collected data that one of our colleagues kindly provided us from a /16 in somewhere in the Midwest. And in this plot, he shows the effect of Nimda worm attack on his particular /16 network. In blue, you see the number of unacknowledged, non-synaptic, port 80 SIMs that are attributed to worm scans. So you see at the peak, and this is rate per minute, at the peak, this chap was receiving something like 7,500 worm scans per minute. In red, we show the total number of unique attackers seen from the vantage point of this particular /16 per minute. So there were moments where this guy was being simultaneously attacked by something like 1,500 machines. And we analyzed who they were too, and they were coming from all around the globe, okay, including, actually the top one was the best one. That was the tax office in the Fujian province, China, okay. The third one was one of the very glamorous networking universities in the United States. So anyway, notice this enormous kind of wave that goes on over a period of a couple of hours and then decays over days. Now, we have come across even more beautiful data, courtesy of one colleague here who's prepared to remain anonymous. But this guy was actually monitoring the router CPU utilization on the access router. That's a big tier 1 provider, by the way. Notice again the perfect alignment. worm scans, what is going here, I mean, I'll explain in a moment, but the Nimda worm goes kaboom, okay? Here we are looking at CPU utilization on a router. This router is big enough so it doesn't conk out. And you see the utilization goes up to 40% from something that's close to 10%, again in the same period of time. Interesting thing, there is a couple of other features. There are 3 strange spikes here, maybe 4. Okay? And you see there are corresponding bumps in CPU utilization. Our interpretation is that whoever created Nimda was experimenting with it in the preceding 2 days. Maybe the worm failed to spread, maybe the worm had a timer and timed out and did not spread on purpose. On the 3rd or on the 4th pass, the guys really got it right. So this is an important plot because this will produce a causal chain. How spread of worms that attacks Microsoft boxes can affect routers, say, from all major vendors, Juniper, Cisco, and so forth. And excessive CPU utilization and excessive memory utilization are going to be one of the mechanisms that we have tentatively identified. So at this point, you see that sending worms to all kinds of guys who are not smart enough and run Windows machines. Well, I run a Windows machine because we're supposed to get stuff in PowerPoint. At least it's not on an, well, it is on a net, okay? But that's what happens, okay? Routers actually do suffer and may suffer terribly if they are not very big. So, now we put these 2 things together. Again, this is this sort of way of looking at multiple peers as rows. These peers come all to the single data collecting router. Instead of showing announcements, as in the previous plot, here I show prefix withdrawal rates. So you see that there is a big wave of prefix withdrawal rates that again coincides with the onset of Nimda spread. And in this case, we actually plot 2 different /16 networks. The second was offered to us courtesy of Vicky Erwin at SANS Institute, and that's plotted sort of in a blue line that trails exactly this red wave. So 2 /16s agree. We have also looked at a few other /16s. They all show the similar qualitative characteristics. Here I'll lead you on to something that I'll go on a little later during the talk, because while, at least for us, the worm spread-induced instabilities were a big surprise, there are other instabilities that people in this community know well, such as, for instance, injecting malformed AS paths, leaking private AS numbers, and things like this. So look back, we put a little sticks here. And you can see that there is sort of little storms or little instabilities corresponding to these sticks. This sticks really measure the intensity of injection of, leaked private AS numbers to AS paths that, as we found out, tend to go without harm through certain routers and cause BGP session resets in other routers. So that's another mechanism of instabilities which is slightly better understood at this time. I'll come back to this point in a moment. At this point, I think we are ready to define what we mean by global routing instability, as opposed to local instabilities or internal to an autonomous system. First of all, that is something that has to show a reasonably dramatic growth. It cannot be some little blip or a single spike, however big. So either we want to see a high rate of route changes in magnitude or in acceleration, say exponential growth, or see enormous variance, say, in withdrawals. That would be better too. We have actually seen it, but that's a different talk. Second, if we talk about global instability, it better last rather long. If it's very quickly dampened, then it's hardly, say, of consequence. It's not nice, but it's hardly of consequence. When we say long times, of course, we mean long relative to the natural scales of BGP. So long, say, to baseline noise or long to the expected time of convergence, if such a thing exists. And lastly, and most importantly, a global event has to show a lot of diversity. And that's exactly why looking at very many sessions at many peering locations or at many exchanges is important. We need to see effects across many peering sessions, in many exchanges. We may also look at them internally to ASs, and then we need to see the big changes in the high diversity of context. For instance, a lot of prefixes are churning, many more than, quote, normally, unquote. Or that the number of routes that we see in update messages, or announcements in this case, is much higher than usual. So there is a concrete definition what a global BGP instability would be. This is a counterexample. Here in this case, that is a few days ago, ASN 1103 went unstable internally. You see, but this is nothing that propagates across all the other peers. Clearly, this sort of very high rate of announcement that stretches for hours is completely dampened by the time it goes to its neighbors and doesn't propagate worldwide. So this is not a global instability. It's one guy going bad. Now we can make it very practical, because, you know, big fancy definitions using dynamical system languages and stuff go only so far, and be very practical. So, global instability. It's an exponential growth in the rate of announcements and or withdrawals. It lasts hours or days, because we think that hours and days is way beyond the expected scale of convergence of BGP, say, at least theoretically. And it has to show large diversity, and we will focus on the fact that a very large number of prefixes should be churning, and that should be seen in our peering sessions with most major internet service providers. Of course, you won't see it from the little rinky-dink networks at the edge, unless something happens to them, but we really look at the big guys here. We have covered the Nimda. You got the flavor. Let's go now and see what happened during Code Red version 2. I mean, the rationale is obvious. I mean, when you have one incident, all that you can derive from it is a philosophical statement. When I have two incidents, I have 2 points, and I can make scientific predictions, right? So let's talk about Code Red, which was a trouble in July. It had a very different time course. Here we show the aggregate prefix announcement rate shown at the RRC00 router in Amsterdam. Okay. Again, each dot is a count of prefix announcements in 30-second intervals. So you see it kind of goes daily cycle, and then daily cycles goes kaboom, factor of 10 up. This is logarithmic scale, so straight line means exponential growth. Hangs up there and takes another 8 hours to kind of go back to normal. So it's not as severe as Nimda, and we know why, but clearly this is a kind of sizable instability. If you rock the boat, say, or rather rock the global BGP system for 16 hours, it's definitely not good news. Again, it was, after a while, we were able to correlate it with the spread of the Code Red version 2. There is some issue about naming Code Red 2 or improved Code Red. That's the one that had the fixed random number generator to get random seeds. So that was covering the IP space during the scan phase much more uniformly. The early Code Red kind of didn't do that much damage because it couldn't scan so well. So again, we see extremely rapid exponential growth. That's why we use log plots, of course, because, you know, it looks like a straight line on a linear scale. The blue shows the number of port 80 scans. The red shows the number of unique attackers. That's one of the /16 networks with whose administrators we have been corresponding and been kind enough to give us fantastic data, TCP dumps and everything from these networks. Again, the rates here are per minute. Now you see the more or less the routine. We like these row plots because they give us a single view on all tiers of a router. And we can, of course, dynamically change it, go to different routers, but as I said, we'll focus on Amsterdam right, because that has interesting tiers. And we look here at the withdrawals. So this is the rate of prefix withdrawals in 15-minute intervals in blue for each tier. And it shows a lot of noise. There are some other things, as you can see. But there is this big wave of withdrawals that goes for hours. Well, that's code red V2 in action, somehow. And as I said, I'll come back to it in a moment. That acts not directly on routers, except few routers with HTTP servers for management interfaces and such, which happen to be attacked or failed. This happens presumably to go by exhausting CPU and or memory and or caches in routers. So, we have gone through pretty detailed analysis of how it breaks down into prefixes. You know, are there some special prefixes that fail more than the others? Are there some peers that are failing much more than the others? Are there some routes that churn much more than the others? The answer is no. The worm attacks did not cause any localized damage. Say, I would say, oh, tier 1, say provider XYZ, fell on the floor, okay, and it created global ripples. That would be a localized event for us. Here, this worm-induced attacks essentially cause BGP session failures worldwide, everywhere, and it's very hard to pinpoint any specific location. It's almost, you know, you look at all prefixes started churning, okay? And that's a separate talk again. A little of explanation, and I would welcome your feedback, because we are not operators. We are, of course, not tier 1 operators, okay? So here is how we understand, I'd say, the distinction between global instabilities caused by massive edge failures, perhaps, such as induced by the worm attacks, and core failures. First of all, if we look at the dynamics of BGP messages, as seen through, say, the changes in the rates of announcements, changes in the rates of withdrawals, changes in route lifetimes, the worm-induced instabilities don't look at all like effects that were well localized and well discussed in the NANOG mailing lists, such as cable cuts, power failures in telco hotels, Baltimore tunnel fire, or the attacks on World Trade Center. They have created effects, and we have seen it yesterday in some talks, and they've been publicized on the net. But these are not global effects. They're fairly localized effects. We have done a bit of research, maybe not more than a bit of research, trying to understand why BGP sessions can fail. Generally, and I really would welcome email to us or remarks after this talk. We have identified 3 primary causes. Router CPU overload, that's similar to the plot of router CPU activity that I have shown you earlier. Routers running out of memory or cache overflows in other routing gear, and software bugs, as usual. Okay. We have received a lot of emails from people whom we never knew, who were extremely helpful after we got /dotted following this posting of this preliminary reports. People were addressing issues such as traffic intensity. I'm slightly dubious myself. I'll tell you in a moment why. I mean, even if you sit at the end of T1 and are as strongly attacked as this guy in the Midwest whose /16 I showed you, at the peak you received something less than 200 SIMs per second. I mean, this is not much. This is not enough to kill a T1. Second, traffic diversity. We think that this is a very strong suspect, okay? By diversity, I mean very large number of flows, very number, say, of source destination IP pairs, orders of magnitude more than usual. Then there were documented cases of HTTP servers and routers going bad when their management port was directly attacked. There were failures in network gear, in particular DSL routers were failing when transmitting worm attacks. There is a very interesting possibility of exporting from the inside of ASs the route flapping that may have been induced by ARP storms, net problems, and all kinds of things like this. And lastly, we also know from anecdotal reports that quite a few folks just pulled the plug during worm attacks. So that, of course, disconnected the BGP sessions. Summarizing, say, primary causes of the worm attacks. At this time, we think that the traffic diversity was perhaps most likely cause of router failures. Again, by traffic diversity, we mean that, say, if normally a router, say, on the input sees, I don't know, maybe 5,000 flows on the average, and then out of the blue it goes to 100,000 flows or 500,000 flows, that would be a big discontinuity, would put a lot of stress on the router. There may be net problems if a router doesn't net. We know of many documented instances of ARP storms caused by scans to non-existing machines. And actually this network, one of these networks that I showed you, the /16s, we have also computed the number of addresses probed within /16. It was about 95% of the available IP address space in the network for 4 hours in a row during code red. I mean, these worms were good, okay? Second, routing traffic itself. That's a very interesting thing because that would be a failure sort of that involves BGP directly, and as well as router architecture and router operating systems. It seems that when the root updates and BGP updates come at extremely high rates at a BGP session in a router can essentially stop processing those. May reset the session, maybe something else happens. Lastly, it is not excluded, although we think it's somewhat less likely, that traffic intensity alone was enough to cause drops of BGP messages, and the sessions were timing out. Let me switch gears. Let me contrast now the worm-induced instabilities with the instabilities with which all of you are familiar and which appear on the NANOG mailing list on and off. Well, I'll show you that they don't appear on the mailing list frequently enough, because it's a lot of that. That's an explanation that we understood talking to people, let's say, on the NANOG community. I have not experimented myself with this, so please correct me if there is some problem here. But roughly, somebody misconfigures a configuration, starts announcing a private number. There are routers in the world that ignore this and just propagate these announcements. That's not what RSC requires. Other routers will see, oh man, I have to contain this thing, and they reset the session. How widely an effect like this may propagate, to some extent depends on what are the routers surrounding you. Will they contain the private AS number leakage, or they'll propagate it to the world? Interestingly, in most cases, this instability will end only when finally somebody calls the guys who did it, and they reconfigure their routers. Couldn't resist quoting Randy, it's not here. I mean, I read it in small print. We have this stick now. Unfortunately, we also have a vendor who ignores sticks. And that's how it looks, guys. This is superimposed on the Code Red v2 worm. So that's what I already explained, this wave of root withdrawals, big time, not root withdrawals, prefix withdrawals, going on July 19th. In the back row, the sticks show the intensity of announcements of this malformed AS path type of announcements. I don't know if you can see, depending on color code. Here we have Digital Island, ChinaNet, Time Warmer, and others, okay? Note that in quite a few cases, leakage of malformed AS path causes kind of smaller in intensity, but quite long-lasting BGP storms or global instabilities. I'll show you a few more examples. That was a particularly bad one. Without naming names, this comes from, our defenders. That comes from DOD, one of the ASs. And this somebody there was just leaking and leaking and leaking for 10 days in June, which was increasing the rate of withdrawals all across the major ISPs in Australia, Europe, and United States by about a factor of 3 to 5, say, for days and days and days. Such things happen. It's a wide place. This is more recent thing. That this instability actually did appear in the NANOG mailing list. Infonet, or rather its subsidiary in the Netherlands, started leaking a malformed private AS number and caused a pretty nasty withdrawal storm, lasting for quite a number of hours and going all around the globe. And there are several others here. We show ChinaNet again, Sao Paulo, which we track back to something like the Brazilian National Science Foundation, which they do a lot of damage all the time. A little bit from net access here, which luckily didn't spread globally, and so forth. So, how should I summarize this? In our view, and I'm really not showing you a lot of our other analysis, which simply don't fit in this time frame. We have barely scratched the surface. There is such an immense amount of information in BGP messages themselves that you can have so many different views on the dynamic state of the global internet. It's really mind-boggling. Okay. Second, I would say let's now enumerate some truly basic findings here. First of all, globally correlated BGP instabilities are common. They are frighteningly common. Some of them, I think we understand to some extent, and that would be these cases, say, of announcing private AS numbers in AS paths and having this propagate and reset BGP sessions. Other effects were unexpected and are somewhat disturbing. This was the Nimda and code red effects. And clearly there is enormous amount of stuff that we can do with this. I think that I should wind down. I want to say a few words more at the end. Some people should receive credit for this. First of all, early analysis was done with DJ Premor, who some of you may know, and Yuan in our place. Our thanks to Henk Eiterwal, who set up the right routing information service. We have received the /16 network data from Vicky Erwin at SANS, Ken Eichmann, and Van Paxson at Assyri. Many thanks to people who are present here and to others who are not here for sending us lots of anecdotal reports, which by themselves were just anecdotes, but when we look at them all together, provided a pretty compelling picture of what could be the causes of global instabilities during the Nimda and Code Red. And finally, I mean, we really enjoy talking to our friends Tom Griffin and Dave Donahoe, and thanks to them as well. Now you see, the possibility of doing analysis like this, to a large extent, depends on collaboration and being able to do research together. We have shown you what we can get with 150 peering sessions, and particularly focusing on large peers. The guy who is kind of more handsome, that's Jim, okay? And this is, well, whatever, okay? I would like to ask you to send us email if you are interested in talking more about it, collaborating multi-hop eBGP feeds for research. And what we'll give you in exchange will be access to near real-time analysis of all the networks that subscribe, in particular your network. May I see a show of hands who would say send us emails today to talk about it some more? Anybody? Thank you. That looks cool. So I think that at this point I would prefer to end slightly ahead of time, and maybe it's time to take questions. Yes, I'm taking questions. I have full 5 minutes that I earned by speaking fast.
I'll just make it a really quick one. So the information that's shared with the other people in the raw feed that get sent to you, there were a few cases here tonight where we actually did have some AS numbers mentioned or specific networks shown on slides. is the information that's shared among anonymized at all? Do you say, okay, we're seeing global instability right now coming from a network, or do you say, AS such and so is causing problems, go yell at them? If we participate with you, is there an expectation that NOC phone numbers, things like that, need to be provided so other members can yell? Or is this just research-based, anonymized, here's the instability, use it as you will, data-wise?
That's an excellent question. I would answer both. It really depends on the arrangement. Some people who are interested, say, in the dynamical properties of BGP, protocol developers, may very well live with anonymized things. Some people who subscribe and receive in exchange the data may, for instance, see their own data in the clear, but other anonymized, or maybe pools of people, and that would be my personal wish, if pools of people come and say, hey, we don't mind if you see our problems and I see your problems. So I think of a kind of an onion of groups with different privileges, and say a general public essentially seeing just a global, totally anonymous view. So it's good for research and concrete data for operators.
May I? A question on your conclusion. You talked about a sudden increase in number of flows, and you thought that could potentially create instability in routers. And I would like to ask, why do you believe so? I mean, any modern router does not forward based on flows. Flows should be completely irrelevant. Only 5 or 10-year-old boxes should care about the number of flows. And even though that should not affect routing as such. So how would the increasing number of flows affect stability of routing on a router?
That's actually a good place to be more specific here. When I said that when the number of flows increases dramatically, it is not about routing. It's about people who presumably run NetFlow on the router. And NetFlow starts using enormous amount of memory and CPU resources. So it's not routing, it's a NetFlow facility installed on the router. That's my understanding.
So the NetFlow gets out of control and makes the router control sleep over and
You see, okay, this is maybe kind of a place to make a one-line hypothesis, followed by, let's say, a question to the equipment vendors. I mean, the internals of most routers are proprietary. So, of course, we have to infer what happens looking at the data and looking at the troubleshooting guides at various routers' websites, which are very detailed and actually do specify cases such that when the number of flows increases very rapidly, the CPU can get starved. When CPU gets starved, BGP session stops sending updates. So here I literally rely in this claim on the basis of troubleshooting guides available on the websites of the major router vendors. I mean, I have not done those measurements myself.
Okay. Another question?
Let me just make one comment on that. What we did observe, and this thing is completely related to NetFlow export, and it wasn't, what we observed was not CPU bound, but bandwidth bound, because those folks who had NetFlow turned on, all the time, who got hit by this, were low bandwidth providers. And so what happened was the flow export filled up their entire T1, and obviously that dropped their BGP. That's what happened.
Thanks, Dave. Yeah.
That's a very interesting data. Another question I would like to raise is concerning, so you're measuring number of withdrawals in terms of BGP, when you consider BGP instability. Did you try to go into more specific what these withdrawals means? Because sometimes the fact that when a single prefix goes down, you can have many withdrawals for that single prefix, And unless the rate is extremely excessive, that should not affect your normal functionality. I mean, do you think that during that high level of withdrawals, you're not going to have service for a valid update?
Okay, so I said it and I repeat it very carefully. We do have capacity of monitoring individual prefixes, okay, over long times. We also look at statistics. During the Microsoft warm storms, Code Red and Nimda, we have seen that virtually all prefixes get withdrawn at much higher rate than usual. So it's not, say, 100, 500, or 1,000 prefixes being flapping like crazy. It is 50,000 prefixes being withdrawn once, twice, or 5 times. That's most stunning. It's not localized.
I'm really interested in this data. Have you tried to look at withdrawals and try to see on the AS tab which point, try to analyze from the withdrawals which point in the AS sequence there was a failure?
We have, and as I told you, we can see localized failures, but in the case of the Microsoft worms, it was widespread. There was not a single point of failure. I mean, maybe we should take it offline because there's other people waiting.
Thank you very much.
Thank you very much.
Perhaps you said it, but I missed it. I was wondering if you knew exactly how much traffic on the backbone had increased. I know that edge providers had problems with their T1s and stuff, but was there a large influx on the backbone?
Okay.
T12 still up.
I think that the people in the audience know much better. We have generally assumed from the relative quietness of mailing lists that major backbones did not really notice much of the worm attack. Notice that Code Red and Nimda do not generate unbelievably large volumes of traffic by transferring files, mass mailings and things like this. They are really self-propagating worms, and the most of the traffic you see is scans, just spot 80 SIMs, okay, that are not answered, followed by TFTP to get the body of the worm, and then everything starts again. Incidentally, I mean, both during Code Red and Nimda, Keynote went on records in multiple publications, worldwide, saying nothing happened to the Internet at all during the worm propagation periods because we measured the backbone and backbone didn't show anything. Well, this is a backbone community, but there is an alternative point of view that users really matter and customers are at the edge. And it looks like customers were suffering very big time. So that's the summary of all anecdotal stories we got by email, plus the plots that I have shown today.
Okay. One other comment. If you appear with Akamai, we'll give you chocolate and data.
Thank you.